Hey gang, I measured out and hand selected 6 pistons for the red Xterra from 3 sets of pistons from NPR. Not how I had idealized it, but it did work out. I wanted to know that I had 6 pistons that were the same size or close, because we've been having so many problems with these pistons. So we did. We ended up with 5 that were the same size and 1 that's about 1/10 larger. So this is the final selection of pistons. I've kind of remarked my box. Originally, this was the set number 2, ironically. So now what I've done is I've grabbed, for example, this was originally number 3 piston from set 4, and now I'm calling that my number 1 piston in this multi-set. I basically took pistons from this set number 2, from this set number 3, and from this set number 4, and fortunately I had all of these after all the long discussion with NPR. I haven't been super satisfied with the consistency of the manufacturing from NPR. I've got tips of the pistons that are wider than the measuring point. I have tips that are narrower. I have tips that are the same size as the measuring point. NPR has told us exactly where to measure these pistons, and I even have an engineering diagram of the piston, of the standard size piston. Technically these are 20 over, but the profile of the piston along the side of it should be the same. So literally, as I measure at this point here, which is 11 millimeters below the tip, I should have my correct measuring point. Sometimes at the tip up here, it's a little narrower. Sometimes it's wider. Some of them were over 1.5 thousandths larger up here, which is ridiculous. As you measure down the piston, the profile, it gets narrower. So that should be consistent. I'll just briefly flash this. I have the engineering diagram, and it shows exactly. There is some controversy because of one spot on there where they talk about, depending on the color code of the piston, what plus and minus should be, but this is, I think they wrote it wrong. +0, +10 thousandths, I don't know, -1 thousandth, -10 thousandths. I think it should have been plus and minus, and the way they formatted it didn't work. But that's not what I show anyway. That's not how the profile changes on these. So whatever their engineering diagram is not what we're getting. So ultimately what I landed with is 6 pistons. I went to the effort of weighing them all. The combined piston and pin, the piston by itself, the piston pin by itself, trying to minimize the amount of work that the balancer will have to do by getting 6 pistons that are close to the same weight. The piston pins were very close, meaning like I'd have a whole bunch that are 99.5 grams, and then I'd have some that were 99.0. So I had to mic out all of those. I used my little 0 to 1 micrometer. I pulled the piston pins out one at a time. I only had one that was slightly smaller, so I decided to not swap one of those. Even though it was the correct weight, it was slightly smaller diameter by about 1/10, which I think 3/10 is what I've heard in the machine shop. I don't think there's any reference to that in the Nissan book, the manual, so I don't know what the correct tolerances are, but I think 3/10 are what they allow. So anyway, what I did was I literally combined
the pistons that are the same size and the same weight, both the pin bore weight and the actual piston weight, to be as close as possible. And I have everything within 1 gram. So they will likely still balance the pistons individually to drop all of them down to be you'll grind a little bit out of each one to match the lightest piston. So they'll be all balanced. But so far we're making some progress now. I'm pretty happy. The only thing we have left to do is measure the deck flatness. I just want to have an idea what the deck looks like before we get started, so I'll have an understanding exactly how much of the deck needs to be removed in order to flatten it properly. So because what we're trying to do is reduce the overall amount of the heads that have been milled and the deck that has been, or the block that has been decked, technically is the terminology you'll hear it.
So what I'm doing here is I'm actually measuring the flatness of the top of this block or the deck. And I wanted to show you this because I went through a bit of a charade with these guys. Technically, I should restate that I went through a charade with Amazon. Amazon's always very supportive. These guys were, I don't know that this device is not accurate, but I wasn't all that happy with the way that it worked out.
What happened is I purchased one of these on Amazon because they were, I don't know, $40 cheaper. I think I got this thing for about 80 bucks, and Central Tool sells them for about 120 if I remember right. And I got it in the mail, and what happened is exactly this.
So when you order one of these, it arrives in this box. Okay, fine. I put a hole in it so I could actually hang it on the wall, as the end of it has a hole here. But this arrived in a box from Amazon.
I ordered one from Amazon that comes in one of those long square boxes.
One of these, okay, it's about 4 inches square.
Problem is, there was no packaging on the inside of it, nothing to keep it from being damaged. And this is actually a really heavy tool. This is a solid piece of metal.
This thing probably weighs 7 pounds, I'm guessing. And it's got this finely machined, precision machined surface, right? So this is how you measure the flatness of this deck. This thing is guaranteed to be only off by 1/1000th of an inch over 12 inches. And this is 2 feet long. So the maximum it's going to be off for accuracy is 2,000. So I can get a reasonably good measurement. I'm only using about half of it or a little more. So I'm going to be off by maybe 1.5 thousandths. And the machine shop will do this more accurately anyway, but I like to know so I can check the machine shop's work. So the problem is, when you get this in the box, there's this plastic guard on here. This is to protect the machine surface. Well, I got one from Amazon, and it was cracked because there was no packaging in the Amazon box.
So I thought, well, oversight. Somebody had an issue, forgot to put packaging in it, just figured it's a long, straight ruler. Nobody ever thought that it's a highly precision surface on there. And that's what you pay for. That's what you pay $100 for, is a machine surface. So I return it to Amazon, and I get another one. Same problem. I thought, no way, that's weird. Just must have been a fluke. Returned it to Amazon, got a third one. Same problem. Then I was like, okay, this is ridiculous. I got to solve this problem with getting one that I have confidence that hasn't been damaged, because if the guard's damaged, the surface could be not accurate, right? So I needed to get a new one, needed to get a good one, so I called Central Tools, and they gave me this whole bunch of mess about, oh, well, if we sell it to you direct, and we have to charge you the $120 plus shipping and all this crap. And I'm like, no. And I did get them to send me just the plastic guard, which, great. So now I've got a plastic guard that's not cracked, but I still don't have any confidence in my machined edge. So I ended up getting, I think, 5. No, I got 6 of these from Amazon. I kept the 6th one finally because I was like, well, they're all busted. They're all broken. And who knows? So anyway, what a pain in the ass. But let's get to measuring and see how we do.
What you do here is you take several measurements. One goes from the center of the cylinders all the way across. Okay. Then we'll do one that goes across that angle. Then we'll do one that goes across that angle. And we'll do that on both surfaces. Always be real careful when you're repositioning this so that you don't damage the surface. And so what we do with each measurement is we use our feeler gauges. So this is a 2/1000, and we just go through here and see if we can fit that underneath here. So right there, that's a pretty flat deck. That 2/1000 doesn't fit anywhere. And the other little secret you can do to this is put some light behind this and see if it bleeds through. Flashlights are never in the spot where I left them. Actually, they're always in the spot where I left them, but they're never in the spot where they go. Funny how that works. Oh, all right, here it is. Okay, here, flashlight. Stick it behind and see if light bleeds through here. None there. None there. And none there. Wow, that's a pretty flat deck. Interesting. Okay.
Well, we'll repeat all these measurements on both the angles and both the surfaces and see how we turn out. There is less than 1.5 thousandths of an inch. That's the smallest feeler gauge I even have. On anywhere on the left-hand side of this deck, it is actually really flat. I was trying to figure out the best way to get the deck level so that I could measure it.
Just gonna put it on the engine stand, and I went through a number of these engine stands that I have. I think I have like 5 of them. Trying to figure out, you know, how to get this twisted in just the right angle. This is a 60-degree block, and it did not match any of the hole placements on any of the 5 engine stands I really have. So this would be a 90-degree angle if you went from here straight up, right? So that angle would be 90 right there. This angle directly down the center line to that deck surface to here is 60 degrees.
And that's what made it so challenging for me to calculate the actual valve timing issue I'm going to have as the surfaces are milled. So the block gets milled or decked, the heads get milled, the crankshaft and the camshafts get closer to each other technically because you're milling and taking away those surfaces. And as you do that on a clockwise rotation V6 engine, you will have valve timing retardation, causing the valves to activate slightly slower than they were when there was the material still that you had removed, when it was still the full depth of the head and depth of the block, which if you can visualize, it's the camshafts get closer and closer down to the crank shaft as you mill those two surfaces away. So what I had to do was calculate on a 60-degree block what that would look like, and it was challenging to do. I had to dig out some of my engineering mathematics.
So for every 13 thousandths of loss that I experience, I'm going to lose about 1 degree of valve timing, and that's on the, I think that's on the camshaft. I'll actually have to double check. The camshafts move at half the rate of the crankshaft, so technically they're affected half as much. So if I actually have a full degree on the camshaft, which is I believe the way I calculated this, I should have only half degree on the crank. And what's more important of this is this calculation on the camshaft, because that's actually what's activating the valves. So literally for every 13 thousandths, I'm only losing about 1 degree. And right now, I think my largest deficit on this motor, I've got 5 on the JDM heads, and I had 4 on the deck, but the grain, it was just too grainy, so we had to redo it. So I've got and then I think Doug took 5 more, which I got to double check. So I've got 9 on the block, 5 on the heads, and we really don't know. The machine shop who did the heads, I think they published the 5 after I complained about the 10 they took off on the first set. So I'm just going to estimate that they're at 10, and we've got almost 10 on the block. We've got 9 on the block. So
I'm going to be off as much as about 1.5 degrees on the camshafts, which isn't terrible. So I think we're going to say that's acceptable. Anyway, okay, well, let's measure the last deck surface on the right-hand side of this block and see what we get.